it may be, I'll put that on, under the carpet. And what else? So this canonical bundle needs to be trivial. And well, for being honest, to really run this model, the physicists actually, they complexified this symplectic form using what's called the B field. So this is our Kähler form, and then you can, you think that it is imaginary, and you can add some closed two form there, but I'll also not touch much on that. I want you to think that we are B equals 0 for me. Okay, and so this is a Calabi-Yau manifold, and for those who haven't seen them, I will give you, I'll give some examples. So in complex dimension 1, complex dimension 1, we do have, we have only the elliptic curves. That for simplex geometers is going to be topologically, it's a torus. In dimension 2, they are all as well diffeomorphic, and they are referred as K3 surface. And the most famous manifestation is the quartic. This equals 0, living inside the corresponding projective space, CP3. And this, and this generalized like the degree n plus 1 hypersurface of CPN is also Calabi-Yau, but let me focus perhaps in the most famous Calabi-Yau, which is the quintic threefold, so the quintic in CP4. And of course, given by similar equation. And well, is the most famous one also because for string theory, the complex dimension of your Calabi-Yau should be 3. And so this is the object that I'm initially going to be talking about. So what's mirror symmetry? So what's mirror symmetry? Perhaps some refer as a phenomenon, philosophy, a religion perhaps for some. So it's the following idea. For each one of this object, so given x, j, omega, there should exist some other Calabi-Yau that will be called a mirror. There should exist a mirror Calabi-Yau such that informally what happens that symplectic information of x omega should correspond to complex geometric information information of X check, J check, and I'm not going to write, I'll say, and vice versa. So complex information of X, J should be equivalent to symplectic information of X check and omega check. And this is because it arrives to two different models for string theory. And when we refer to the symplectic information, we usually it's called the A model. And for complex information, it's called the B model. So the first kind of like mirror symmetry that was studied that arises refers is some sort of Hodge theoretical mirror symmetry that I'm not going to touch too much upon here. We're going to focus definitely more on homological mirror symmetry. But I do want to mention the famous example. So the first prediction arises for using some isomorphism of between the Hodge group associated to X with the ones associated to X check, essentially one that should encode the variation of simplex structures here and one that should encode variations, infinitesimal variations of complex structures there. And then within this isomorphism, it was also expected to have some relations between two types of couplings defined on this space that they are referred to Yukawa couplings. So here I'm just going to mention the following. So this Yukawa coupling on the A side on the A side, it encodes information of genus 0, Gromov-Witten invariants of X omega. And here I write X omega, even though Gromov-Witten invariants are defined by a choice of J. So if you use J can be almost complex, and if you use different J's, provided they're regular, this should be invariant. So it's actually an invariant for the symplectic information of your space. And this, so for those who doesn't know what Gromov-Witten is, it encodes counts of genus 0 complex curves, also known as rational curves. So essentially CP1s embedded in your manifold. And it just so happened that the Yukawa coupling that is supposed to be equivalent to this on the B side, I'm not going to tell you much, but it involves some integral related to some Gauss-Manin connections and so on. It involves some sort of integral, but the focus point here for me is that this part here is really hard to compute. It's really hard to compute. So then if you manage to find a mirror, so these integrals here, even though I haven't computed any, this is supposed to be easier to compute. You can run your computer and compute them easily. And that's what was done for the quintic. So when X is the quintic, so this is the first example that really started mirror symmetry, at least for mathematicians. For the quintic, we have the famous work of Candelas, De La Ossa, Green, and Parks in the Parks. And so what they did, they essentially, for the quintic, they constructed what for them they constructed the proposed mirror and used it to compute they used them to compute the this one's not so good. The Gromov-Witt invariance for the quintic. Or at least, I mean, since it was not actually proven, the actual mirror symmetry, the isomorphism between the Yukai couplings, what they actually did, they predicted so in the quintic we have only one-dimensional H2, so they predicted degree D, they predicted ND, which is the number of degree D rational curves. So what should I? G equals 0. Well, G equals 0 curves in the quintic. So the first one is 2875, and I believe I managed to memorize the second one as well. So I'm for those that think I'm not as good as Gugu in memorizing numbers, actually far from that. I believe it's this. I'll just double check. Yes, and this was in the 90s, actually 1990. And well, they also computed NE3 and so on. And what happens is that some mathematicians have computed some of these numbers, and this I need to choose the name. So the history goes that some people noted that these numbers didn't match some computed numbers by, this was just one end or two ends, Ellingsrud and Strom, and they just start saying, oh, this physics is not rigorous, it's like bullshit, or so on, so on. Some mathematicians, of course, I'm paraphrasing probably. But what happens is that then they went back and double checked, so they have used computer codes to compute these numbers. So they double checked it, and in the end there was an error on their code. They corrected the error, and the numbers matched. I don't really remember which number one was the one that didn't match.
So in this setting, the correspondence that was expected is that the Gromov-Witt invariants are equal to these intervals of.
This is part of it. There is a correspondence between age PQ of X should be isomorphic, I hope, I'm not mistaken, but there is some correspondence of Hodge theory. So for threefolds, it's kind of like so the name comes from that. From threefolds, you do the Hodge diamond, and essentially you take the diagonal or the anti-diagonal and reflect the Hodge diamond. The Hodge diamond of one should be the reflection of the Hodge diamond of the other. And within age 11, there is this information of variation of complex structure that this Yukai coupling encodes this sort of formation, and there is a similar Yukai coupling for the isomorphic space here that should compute some other integral. And then if you understand the isomorphism well, then these two are expected to match, and that's how they predicted these numbers. So, so for this kind of Hodge theoretical mirror symmetry, that's what I want to say. This was very much a revolution in mathematics, that we start to believe in the physicist again. And then I want to jump some 4 years to what I'm sure Elsie will briefly present in more detail, which is homological mirror symmetry. I need to, it's some singular quintic that you resolved. I don't remember how many points. Do you remember, Elsa? Yeah, the mirror of the quintic. I think there is 3. Well, I don't want to try to remember. So,
I have one question. What about the existence of the mirror? Is it guaranteed?
no, this is a conjecture. This is essentially a conjecture. This is or the philosophy of phenomena or whatever. And then then what it means to be a mirror? There is the Hodge theoretical version of it, and I'm going to introduce you the homological mirror symmetry version of it. That, well, one also expect perhaps to imply the other, but it's not this too much. It's a lot of work in progress. Homological, I have written, could have just write HMS, but homological mirror symmetry. I'll just abbreviate this one. HMS, and as I pointed out before, it was due to Kontsevich. It was due to Kontsevich in '94, and the idea comes from again from physics. So particles should be these strings that are vibrating inside your calabial, but then you have closed strings that they can vibrate probably whatever way they want, but then you have open strings. These open strings, within your theory, there's some sort of boundary problem that they need to minimize some integral. There is some boundary there, and so their boundary, they are not free to move in whatever way they want. They need to be restricted to something called D-branes. So the boundary of your string should be restricted to what physicists name D-branes. And so in the A side, in the A model, the D-branes are Lagrangian submanifolds of, well, of your space, of your labial, and equip it with flat vector bundles on them. And on this side, they are supposed to be complex submanifolds. The B model, they are D-branes are complex submanifolds yes, of xj equipped with holomorphic vector bundles. That's what physicists would tell you. So then, based on that, Conseil stated that some category that involves these objects here should be, in a way, equivalent to a category that encodes or contains also these short objects. And this is what I'll briefly mention here, and it's also part, and I'm sure, this one I'm sure I was going to speak a little bit with some more detail than myself. So Fukaya categories is not actually a category, it's what we call an A-infinity category that whose objects are Lagrangian submanifolds of your space equipped with some structure. For me here, Lagrangian for me will always be, at least mostly be, tomorrow they may not be compact, but today they will be compact. This afternoon, compact, oriented, and spin for some technical reason. And Lagrange submanifolds of X omega equipped with, well, somehow we can, because we're going to somehow derive this category to obtain this object, it's expected that we can just, the easiest version for this, it equips with local systems that can just think of them as flat connections on trivial line bundle. And unitary. Unitary. And flat, well, flat U1 connections on L cross C. I hope everyone is on board what this is. And morphisms, I can start perhaps right here. Morphisms are floor chain complex. So morphism between two objects are the floor complex between two Lagrangians. Even though they're equipped with these local systems, I'm kind of like gonna omit them from the notation. So Fourier complex of these two Lagrangians, and these are generated by points of intersection. So assume, well, assume that L1 intersects L2 transversely. So just recall for those that start seeing on Monday what symplectic geometry is. Lagrangians, they have half of the dimension of your manifold. So you have two objects that have half of the dimension of the manifold. If they intersect transversely, they will intersect on points. So this is generated by these points on L1 intersect at L2. So this category essentially should encode intersection theory of these Lagrangians. And the corresponding category that one could think that also encodes intersection theory of the D-branes on the B side is the category of coherent sheaves. And I'll definitely not go much into detail, try to define coherent sheaves, but the way I think of them, and then I think you should think of them, is the following. So the objects, I'll not write again, the objects are coherent sheaves. Okay? But coherent sheaves, I want to think that this includes algebraic or complex submanifolds of X endowed with a holomorphic vector bundle over them. And so it includes these structures and perhaps the generations, how these things degenerate, and morphisms. So morphisms are usual homomorphism of sheaves. But then you also want to derive these things, so you actually get these extensions. And perhaps you should vaguely think that this should correspond to intersection theory. On XJ. Okay? So now I'm going to give you the precise.
Is this a genuine category or is it also an
This is the genuine category. Then there is this thing about deriving things, and deriving infinite categories is different than.
I mean, is it a category in the sense of category theory? Like,
It's because like you take some sort of homology that then they will match after you derive these categories. Deriving categories here, I'm not sure if I was going to explain it in detail or not, but it's a little bit different than. Intersection theory are Holmes and X. When you derive, you get X. Yes. So Kontsevich homological mirror symmetry. Perhaps I can even write down here, not to write the title again. So the precise definition is that the Fukaya category of x omega, and you somehow enhance this category and take its homology. So we can use this terminology. dB of the Fukaya category is dB of the category of coherent sheaves of X check, J check, and vice versa. So I didn't actually write a statement, I guess, but let me. Let's leave the checks there. So dB co xj should be equivalent to dB Fuk of X check omega check. So the main. So what should be the statement, or this is homological mirror symmetry conjecture? And the conjecture is that, right, given X, there should exist a mirror such that we have the above. Okay? And, well, now what I ought to explain to you, and we want to focus a little bit more, it's going to be the more technical part of this, is, not now, I still want to talk a bit of, I said I would say some words about SYZ, but then, of course, this Floer complex is what gives rise to Lagrangian Floer homology. And after you, sorry, on the second part of my talk, I want to explain this in more detail. But for now, I want to give you some flavor on how people go about trying to construct this mirror, and this comes as is known as I'll erase here. So you have some geometric interpretation on how these things came about, and it was done by Strominger, Yau, and Zaslow, and it's known as the SYZ conjecture. That states that there should be, so you have your Calabi-Yau, there should be some fibration, some Lagrangian fibration, and actually special Lagrangian torus fibration. So this, I'll write the names, but I just think it's some fibration by Lagrangian tori. On X, and the same on X check, but with the Lagrangian tori in X check actually being identified with the dual torus on L which is the homomorphisms from your torus to U1 and of pi 1. And well, of course, you know this is abelian. This is H1 generated by n elements. So this is indeed, you just, if you want one of these, you need to choose n points on the circle. And so the conjecture is there should be this vibration on the base such that x check is given by this other sort of vibration, and then this really started things. Probably a lot of people like Gross-Seibert. I didn't talk about wall crossing, but yes.
So, and in here they are special Lagrangian with respect to the
You choose. No, you choose your omega. You choose. Your metric doesn't need to be rich flat as far as I know, and then you choose one trivialization. You choose a complex volume form, and then you special Lagrangian with respect to this complex volume form.
I understand you don't care about the metric, but you care about x omega, x side, and then x hat, j hat, the other.
Yeah,
But I think for the physics it's important that
perhaps. For simple geometry, not so much. You choose an omega that you should find this, and this very much a conjecture as well. And well, we have a lot of examples, but let me. What do I want to say before this? I wanted to give you a remark here. I just remember I forgot to give you a remark that. Homological mirror symmetry has been extended beyond Calabi-Yau, and then, for instance, for funnels, and the structure needs to change a little bit, but we are extending this theory beyond Calabi-Yau spaces. And here I would like to add some remarks. First, for instance, this I learned from Denis. I think was him who actually came out with this. And so if you start, say you then start with a special Lagrangian vibration on your manifold X, then you can just consider X check as this space of Lagrangian submanifolds endowed with these local systems, and then after you build this space, then you can actually then it goes on and construct. Tells how you can see this as a Kähler, as a Calabi-Yau by constructing j hat and omega hat. Was he the first who came out? Because I learned from the 07 paper, but this seems to be too, perhaps it was known before.
I would guess it was understood. Something he would say that it was understood.
Was understood before, yes. So perhaps it was generally understood, but not written. But what I want to mention is that this gives you a recipe somehow for constructing this space. But one important remark, there are actually two, but I don't want to talk much about large complex. There's some sort of this should work in some sort of limit. But one important remark is that besides, if you're not on the one-dimensional case of the elliptic curve, you expect you must have singular fibers. And the presence of these single fibers makes the theory, if you will, a little bit more interesting. To construct this space, you need to use some sort of wall crossing formulas. And some people even refer them based on where's Gonçalo? Based on gauge theory. People also refer them as instanton corrections. But as far as I understand, it's just a name that comes from a similar behavior when try to understand moduli space of instanton. And so this. So this is the origin of some very famous work. Perhaps I'll just cite with Gross and a lot of people, but perhaps I'll cite Gross-Zibert program. To construct the mirror and understanding the behaviors, there should be ... here. And okay, I'm close to the 10-minute break. So yes, this is just, I guess this is all I want to talk about. Let's see if I want to give, if I miss some remark. Oh, the other remark I kind of said didn't write, but that Fukaya category is actually an A-infinity category, and we'll see this afternoon what this means. And so I'll stop here for the 10-minute break, and then we start back, and then I'll be talking to you and defining Lagrangian flow homology. Okay?